Good. Well, morning. Welcome to this second series of webinars on spatial data science topic. And this let me recap just this concept of spatial data science, just a short words. The spatial data science is a branch of technologies and the models, just that combines the data science methods like machine learning, artificial intelligence, and so on, with spatial analysis methods like geographical information system, geostatistics, image analysis of satellite, and so on, in order to understand and characterize physical phenomena with spatial patterns. Okay, the applications of spatial data science is growing up a lot in those moments, but goes from I would say geophysics, satellite imagery analysis, economics, social science, until public health, and so on. It's a lot of applications, and actually, in this moment, there's the number of companies that are adopting spatial data science methodology at its core is also growing a lot. Okay, but coming down to our first seminar, let me tell you that this series is a series of seminars that will be held exactly every Wednesday, starting today until up to 8th of June at same time, 12:30. And and the first one is Ana Oliveira, will be given by Ana Oliveira, which is here, and is about the spatial data science applications to urban climate. Ana, the stage is yours.
Thank you, Professor. I will start sharing my screen. Okay, think everything is okay, right? Everyone is seeing correctly? Okay, so first I would like to thank you, Professor Amilcar Soares, for the invitation. He worked alongside me on my PhD thesis and supported me throughout my journey. So the results that I'm going to present today are not only the results from my PhD thesis, but how it evolved afterwards. So I would like to acknowledge all my co-authors who are listed here in the first page of the presentation, and they come from several entities, from Técnico, CERENA, up to IGOT, the Institute of Geographical and Territorial Planning, and also Plus Atlantic, where I work now. So the motivation for the work that I have developed so far, and it started a long time ago, more than 7 years ago, is related to the societal challenges, climate change, the aging of population, and specifically focusing on coastal regions in Europe, Southern Europe. So it's more of a common sense that more frequent and intense heat waves are expected in the upcoming years, and they are already registered in the later decades. It's also known to us that our Europe population is aging, and this has an increased impact from heat extremes due to the sensitive health of the elder. And also, oh, sorry, I have this in front, okay. So, and also constraints on local climate adaptation capacity, since Mediterranean countries are have lower income and lower economic conditions to adapt. So the premises or the assumptions that I've used in my PhD thesis and that have evolved in Plus Atlantic is to look for computational efficient methods, also that are scalable to other European functional urban areas, and low cost to local authorities. So I'm looking into efficient and low cost methods that don't have to be the most accurate and physical based, but that can provide a low cost solution for municipalities and local stakeholders. So in that regard, I have opted for using empirical and machine learning approaches using open data from Europe and remote sensing free satellite imagery, and open science approach using open languages, programming languages. The aim is to map heatwave exposure at the local level by downscaling regional context weather variables, in particular temperature, and this to provide scenarios and climate change adaptation strategies. So still in the motivation scope, we all know that the heat waves have an impact on health, especially the elder and the children. They provide an increase in mortality during this summer that can reach up to the levels of COVID daily mortality, even if during a smaller period. But we also know from established literature that there is something called the urban heat island effect. The urban heat island effect is a temperature increase in artificial land cover context, specifically where built-up infrastructures are quite dense. And this is a result of a lower heat loss from latent heat fluxes due to the absence of vegetation, and also an increase in heat storage due to artificial materials and heat capacity. This effect is typically negative in the atmosphere, in the lower atmosphere during the day, and positive during the night when the stored heat during the day is then released to the lower level of the atmosphere. I'm describing this effect because this is the cornerstone for the research that I'm going to present. Just to frame heat waves in Europe, this is a recently published paper that shows an algorithm to establish a ranking amongst larger urban areas in Europe and how these are exposed to heat wave events. And by exposure, we mean the interaction between the normalized amount of people above 65-year-olds, the ones that are more at risk, multiplied by the probability of severe heat waves occurring. And severe heat waves are those that are even above the maximum percentile of heat waves levels. And heat waves are already above the 90th percentile. So these are quite extreme. And we can see from the map above that in Lisbon, southern Spain, Italy, but also in Central Europe, the probability of severe heat waves in the last decade is quite striking, up to the 100%. This means one extreme heat wave per year at least. But the issue here is where, what is the effect we are trying to map is the air temperature exposure, and we are trying to discriminate between neighborhoods and urban areas, what temperature levels are registered and how to acclimatize our cities. So the issue is the where and the spatial resolution. And the case study that I'm going to present is the Lisbon metropolitan area that is characterized by several features. So this is a coastal and estuarine region. We have a quite dense and older urban land cover class in the Lisbon city center. It's more or less here. We also have some urban parks and green infrastructure structures or features, but we also have like a finger pattern of urban sprawl to the inland mixed with some agriculture land cover, and all these brings forward a complex set of factors that determine local temperature to downscale it from the regional processes. To do this, we are constrained by observation. So for a machine learning process to be good, it is necessary to have good observations, and the machine learning model can be only as good as our observations. The fact is that we have very low number of stations available, official stations available. Here in green, we have the official ones that are reported in Ncdc by NOAA. These belong to the official weather World Meteorological Organization network. And we also have some municipal stations such as this one. They are increasing, but they are not that much. But what we do have now is citizen-acquired stations. And in particular, there is the Netatmo company who provides €200 sensors that can be deployed by anyone. And there are hundreds of stations deployed in Lisbon. The issue with these sensors is that they are not necessarily accurate. So we also know from the literature that, for instance, from what would be the typical statistical distribution of observations of temperature, including those that are official, there are a lot of observations and stations that are outside of the expected range. This can come from a number of problems, mostly related to how these sensors are installed. They can be in verandas, they can be inside. Some of those are deployed indoors, while it shouldn't, and others are exposed to solar radiation during only a part of the day. So we can see a spike during that hour of the day. Others are permanently in the shadow. So a routine must be conducted before any kind of training data set is built from the response variable side. In this regard, we employed the methodology developed by Napoli et al. It is a statistical method by which we eliminate stations that have very poor readings outside of the statistical distribution, and even those stations that are kept. Each observation is compared to all the others in a specific region of interest that can range from tens of meters to 100 meters, depending on the user choice. And as a rule of thumb, about half of the observations are garbage. They must be discarded before conducting our machine learning model. So after employing this quality control, these red dots are the number of stations that have at least one observation that could be used for the training as a response variables. The ones that do not have a red dot are discarded, but even in those stations that are approved, there are a lot of observations in that station that must be discarded as well. So what we have currently in Lisbon is the official Ipm Forecasts. So Ipm is our national weather agency, and they provide numerical model-based forecasts of temperature. Sorry, I will repeat it. This is from the AROM model. It's a model that outputs the results in 2.5 kilometers resolution. And as you can see from this image, the pixel is quite coarse, and it does not provide specific differentiating values between areas that we know, having experienced weather here, that must be different, such as Sintra, Serra, sorry, I'm not occurring the name, and as well as the city center of Lisbon. So here at Plus Atlantic, we have been developing a downscaling model that has to comply with several user requirements that have been stated by municipalities and final users that we are working with. So what we want is not only to develop a machine learning model that I'm going to present, but also to ensure some certain degree of accuracy that has to match at least those provided by the official weather entity, Ipm, that also has to be consistent available. So our inputs must be consistently available as well. That ensures subcolorimetric resolution so that we can distinguish between neighborhoods, green parks, etc., and for urban planners and urban stakeholders to distinguish risk and exposure levels. That can provide early warning triggers for cold and heat extremes according to regional conditions, but also can provide high resolution climate change scenarios, and those are more meaningful to the urban planners to test the implementation of further green infrastructure and how much it can cool a specific area. And this is to be provided through an efficient user interface and user experience solution that is currently being developed and is going to be published soon in the next weeks. And all the back end and front end has to be coded in such a manner that it is low cost. So the overall reasoning, not entering into the complex physical aspects involved, is that our hourly observations after quality control, and these are the official ones that are very few, and the citizen acquired ones that are subject to quality control, is our response variable. And it is a response, it is modeled in such a way that it is a response from the accumulated effects from the background conditions, and this is retrieved from AROM, not only temperature, but also other basic essential climate variables such as mean sea level pressure, relative humidity, but mostly important wind direction and speed. Also landscape effects that we know from the literature that have a great influence at the local level when we downscale to the meters resolution. This does not have only to, this is not only the digital elevation model and altitude, but also variables that determine the interaction between, for instance, wind and the topographic exposure that changes in each time step according to the prevailing wind direction. Also latitude and longitude and coastal and river distance, which are proxies from the influence of land and sea breezes depending on the hour of the day. So, in addition, we have the urban effects. So I have mentioned before the urban entitled effect, and this can be predicted using tree cover percentage, imperviousness, or Bowen ratio, which is a ratio between the sensible heat flux, which is the heat flux that we feel in our skins per se, and the latent heat flux, which is the heat loss due to evapotranspiration via green infrastructure. So this is the basic physical reasoning. The plus here is only symbolic because we have used a random forest model, so it's not necessarily a linear sum of these aspects. So the general workflow retrieves data from a lot of sources, starting from Copernicus data, which is used to convert land use and land cover as is to the Bowen ratio discretization, also land surface temperature and the correlated energy fluxes depending on the hour of the day. Also the regional conditions, which are retrieved from Ipm, as I mentioned before. Observations are those that are official and also from the NetAtmo devices that I mentioned before. And then we have some kind of domain knowledge a priori that allows us to choose best our candidate input explanatory variables, but all of these, let's say our big training plus testing data set is subject to some kind of exploratory data analysis by which we shortlist the variables, we transform those that require transformation. For instance, coastal and river distance must be transformed into logarithms because the distance does not have a linear effect, even though machine learning models, nonlinear ones, sometimes understand and learn that kind of nonlinear relations, and only then we go through an iterative process by which we test different models, we compare the results, and in this stage we already separated our training and testing data set, and we go back and forth up to the optimal solution is provided. Nonetheless, the CoastSense project, the final aim is to provide an efficient model to the final stakeholders or users, municipal ones mostly, that can provide them situational awareness and the prioritization of adaptation responses during temperature extremes. In terms of input data, we worked with a huge amount of data from NetAtmo and Ncdc. We have used 70% of data for training and 30% of data to testing. The way we constructed our training and testing data set was by predicting or testing the results in the later stages of the time series, but we covered several years in order to ensure that we have the seasonal curve. And the 30% prediction testing data set is not in the latest 3 months as is depicted here. This is just for visual, easier interpretation, but it was like the last week in each month would be for testing only. so that we are not over adjusting to the training data and getting all the seasonal curve. And now in 2022, we used the data, the new data only for testing, so no training. As a recap from the stations available, these are the ones that were used for training and testing. So some of those, such as the red ones from Netatmo, were used for training and for testing, but only for temporal validation. So the same station was in the testing and the training data set, although the time series is not. Then we have the bluish ones. These ones were used only for testing. So the model does not know these stations. It has never seen them because they have been deployed only this year in Lisbon. And this is a good playground to test the model spatial predictions. And then we have Ncdc stations, which are more or less the same as Netatmo for temporal validation. But these are background stations, and the need to use them is because we want to improve urban predictions without overestimating significantly those predictions that are not urban, that are rural or background stations. So this is a sample of the results obtained so far. This is the cumulative density distribution of the errors from both AROM and random forest. The reason why we plot these two models is because the random forest 8, which is our, and AROM, which is Ipm, although this is AROM interpolated. So we assumed that using, actually we conducted both validations, but for presentation purposes, we chose to present the results with AROM interpolated because it is the one that has the same resolution as the random forest, but it is a simple spline interpolation based only on distance and not covariables. So it is the more meaningful to compare. And considering these numbers of observations, we have improved the overall accuracy compared to Ipm. We have seen a reduction that is in the decimal degrees Celsius level. This difference has a seasonal curve indeed, so we can see that the improvement is better in some periods of the year, and we are going to see that better next. I would love to close this menu, but I can't. So this is a time series plot, just a sample during January 2021. This was an extreme cold event, and you can see in blue the Ipm forecasts, in black the observations in these cities, and in red our model. And you can see that depending on the city, there is an overall shift that is not the same during every hour of the day. It is mostly during the night because it's when the urban heat island effect is present. So it's where AROM fails to predict in urban areas, and it's more adjusted to the observations, in some locations better than in others. This is the same reasoning but during an heat extreme. And as you can see, the results are not as good, although there is still a slight improvement. Then we also compared with the Lisbon urban network that I mentioned before. This network is a quite dense network only in Lisbon municipality, and it is the network which stations did not enter the model. So it is like a big trial for us to see now in 2022 with temporal data that did not enter the training and stations that also did not enter the training, to compare what is the relative difference or improvement of our model compared to AROM. And what we saw, and here I'm plotting against the hour of the day because I don't have a seasonal effect yet because we haven't finished this 2022 year, but you can see the improvement curve in red compared to AROM forecasts, and how our error is reduced mostly during the night, while in some instances it is worse during the day, during the warming phase of the day. But when our model's performance is worse, the difference is not as striking as our nocturnal improvement. So it provides us with an argument that our model does indeed provide what we aimed for, which is to predict the urban heat island effect and helping differentiating the neighborhoods. These errors are all plotted comparing a single point of observation or time series of observations with the pixel in which this point is located. So in terms of spatial patterns, I provide you here with a snapshot of the results. These are two time series, one from AROM on the left, the machine learning downscale model on the right. And you can see that not only the pixel size is different, but also the details that are depicted in the model. For instance, for all of us that are familiar with Lisbon, we can see the cooling effect in Monsanto, which is at a higher altitude and covered in trees. But in the next slide, I'm also going to present a single time step during an heatwave event in Lisbon. And this is the forecast from AROM. And here you cannot see the urban effect at all. You can only see the gradient that comes from the continental air masses flows. But when we go to our model, we can definitely see the spatial pattern from both the topographic exposure, the topography, but also tree coverage here in Monsanto, and smaller parks that we are aware that exist in Lisbon, or areas that are less dense and thus a bit cooler than their surroundings. And you can also see the warm up in the main built up areas of the city, while not losing the effect of the continental air masses that are warmer during the late afternoon hours of the day. Now, this is just a sneak peek of the platform that is going to go live and public in the next week. So right now, this machine learning model has evolved to operational stage. It's currently a beta stage, so it's running daily. It's using AROM as its daily input, and we provide the predictions every day for the next 24 up to 36 hours. Currently, the platform does not have these excess heat or excess cold indices. This is going to be still developed alongside the municipalities in the Lisbon metropolitan area, should there be an opportunity to do so. But what is already available in the platform is the air temperature predictions and the corresponding spatial thermal amplitude, because since air temperature varies a lot throughout the day and the year, the absolute scale is difficult to interpret the spatial patterns of the urban presence. So the thermal amplitude layer provides you with a difference from the mean that highlights which areas are warmer or cooler, and how does that relate with built up infrastructure or green parks. The next steps of the research will involve the development of those layers that I've mentioned before, their temperature anomaly, excess and cold factor, and the cooling heat or heating degrees. These are used for diverse set of applications, from climate and climate change analysis to health impact assessment, or to cooling and heating acclimatization and energy needs. So our aim is to provide these sector-specific indices that can be used for a further impact assessment application. And finally, our aim is afterwards to conduct an analysis similar as this one that has been conducted only for Lisbon in the scope of the PhD, which is to adjust our predictions to several scenarios of climate change and urban development and urban growth or green infrastructure introduction, to see how much those changes provide urban heat island or cooling heat island change as well. So this has been my presentation. I hope you enjoyed, and please feel free to ask any questions you see fit.
Thank you, Anna. Very nice presentation. As Anna said, we have some time for questions. Just while these people is thinking about the question, can you?
I think
there's one. Rita, do you have a question?
I think she was clapping.
Clapping, not
Yes, yes, I was clapping.
clapping. Okay.
Congratulations.
She is a co-author of the study, by the way.
Okay. This method that you mentioned several times of Ipm arome, it stands for what? Autoregressive or what is this?
AROM is a numerical weather model, so it's deterministic and physics-based.
Okay. So
I use it only as an input for weather forecasts. So it frames my downscaling, let's say.
Okay. Just for other people to understand. Another thing is when you try to predict, to forecast in a given station, in a given city, for example, for tomorrow or after tomorrow and so on, with how many periods you took from historical of this place.
Okay, so we don't have a regular grid of observations training the model, but we've used data since 2019. So it's more or less 2 years worth of data, although 30% of that was kept for testing.
Yeah, but when you try to forecast for next day or next week,
okay.
How many days in advance you took?
No, only 1 day or 1 day and a half, depending on the hour of the day when AROM is released. But typically, it's 1 day and a half at midnight. But most people are not at midnight looking for the next day weather. So let's say 24 hours in advance.
Okay, good. And it's quite amazing when you compare the results with Ipm. I'm sure that Ipm will adopt your model.
Yeah, we actually were talking with Ipm yesterday, and Fabiola here, she's also working there, and putting the issue more on a broader scope, the machine learning application is really bridging this gap between the numerical models and the local scale phenomena, because in fact the machine learning model cannot learn the complex weather processes that are physical based and are computational demanding. I mean, the model wouldn't work without AROM. Let's put it bluntly, but having those physical based processes that are global or regional, accurately or as accurately as possible predicted, one can then downscale and adjust the existing bias to the local observations. For instance, we have detected that AROM has a consistent bias of underestimation during the night. We also know from physical processes that this is probably due to the urban heat island effect and the heat being transmitted to the lower atmosphere during the night. So it makes sense for us to use urban and artificial land cover predictors to bridge this gap. But if one was to use a numerical weather prediction system to do this, as we have done, in terms of computation, it would be hugely demanding to do it for the full metropolitan area or even for the country for that matter. And machine learning models can bridge that gap because it's not that complex to make that last mile between the regional complex processes and the local easier to grasp ones, I would say. But I don't know if the meteorologists here want to contest what I'm saying, because there's usually this huge debate between people from numerical models and people from data science. So
exactly. So, but let me know one thing. All the cities that you have shown, when you compare your model results with the reality and the aroma results, in all those cities, you got stations with historical data, right?
Exactly.
Okay.
Yes.
There's no situation where you interpolate stuff. No, you presented just those where you had training and historical data. Okay.
For validation purposes, yes. But for predictions, yes, I necessarily have to bridge the spatial gaps between stations because they are not homogeneous in the territory. There are places where there are very few stations.
Okay. Okay, people, folks, more questions. There's any more questions for this very interesting? I know that Hannah is usually very clear, but for sure there's some you have some doubts about her presentation. Okay, Hannah, no doubts, no questions. Let me thank you. This was an excellent presentation, very clear, and I'm sure that your further work will bring us another achievement, interesting achievement. Thank you so much.
Thank you very much. And I would like to make some publicity to follow the LinkedIn from Collab Plus Atlantic, because we are very enthusiastic about publishing our results in our platform during the next week.
Okay, and this section that was recorded, I will make it publicly available very soon. Thank you so much. Okay.
Thank you.
Bye-bye.
Thank you.
Bye-bye.
Bye.
Bye-bye, everybody. Thank you, Anna.
Thank you.